Hello everyone and welcome to my YouTube channel. So today we will talk about a paper called Denoising Diffusion Probabilistic Models, which is one of the first paper to theorize diffusion models for image generation. It was published in December 2020 and is mainly based on a paper published in 2015 by Sol Dickstein et al., whose name is Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. And so I want to talk about this paper because it is one of the foundation papers in diffusion models, and as you have probably seen in the last 2 or 3 years, image generation has become really incredible with products like Midjourney, DALL-E, Imagen and company that you may have encountered, and that always produces better and better results. So before diving into where the theory now is, I would like to come back to one of the pioneering papers, which is this paper published by Jonathan Howe, A.J. Jane and Peter Abeel, all from the UC Berkeley. So let's start with the abstract. So here they present a high quality image synthesis using diffusion probabilistic models. We will come later to what this means. And so here they claim to have on the CIFAR 10 dataset an inception score of 9.46 and a FID score of 3.17. And so they claim to obtain sample quality similar to progressive GAN. For those who have heard about GAN a bit before, progressive GAN was a new architecture proposed by NVIDIA. From memory, it should be around 2017. And the specificity of this architecture is that, well, one of the main problems when using GANs is the convergence of the algorithms. So if you want to explain quickly what a GAN is, basically it will sample some noise Z from a latent space and then do several operations. Well, I won't get into the architecture details, but do several operations, for example, upsampling, using convolutions and stuff, to generate an image. And then this generated image will be fed to some discriminator, what we call discriminator architecture, which will tell you, okay, is it a fake image or a real image. And so the problem, and so to train these kind of architectures, you basically, well, train your generator to generate realistic looking images by sampling some noise Z here, generating an image, and then sometimes give to your discriminator a real image, and sometimes give to your discriminator a fake image. And so the objective of your discriminator here will be to say, okay, to determine if the image is real or fake, and then the generator will need to generate an image which will fool the discriminator in saying whether it's real or fake. So they have opposing objectives, and basically it has been theorized that there is a unique solution where the generator is able to regenerate to fit the data distribution of the training set and then create images that will fool the discriminator. Anyway, that's not really the point here, but so when they say they obtain similar image quality to progressive GAN, well, progressive GAN was built at the moment where the main problem with GANs was how to make these models converge. And to help this model to converge, NVIDIA proposed an architecture where they would still use this generator and discriminator architecture, but instead of having a generator that will directly produce your high resolution image, for example 256 by 256, well, they will create a generator that will gradually build bigger images. And so the first image it will generate will be, for example, 8 by 8 image, and then resize the images of your training set to feed to the discriminator. And then once so this fed to the discriminator, and then it says whether it's real or fake. All right. And basically, once this discriminator has converged, so this couple generator discriminator has converged, then it will build 16 by 16 images. And so in this way, they have shown that they have less problems with the convergence of the algorithms. But anyway, there has been a lot of research about GANs, and so generative adversarial networks, and convergence is always a thing, right? And here the reason why there was such a big leap in image synthesis was this appearance of diffusion probabilistic models, which is another kind of architecture for that we could use for image generation, and which is also used for sound generation, audio generation, I think. And so which is a very powerful architecture, and powerful in the sense that it doesn't suffer first of all of convergence problems, so which was the main problem of GANs. And now I think, well, we will come back later about the problems of diffusion models, but anyway. So here they claim they have an inception score of 9.46 with a FID of 3.17. So let me quickly go back to these notions of inception score and FID. So what is the inception score? So Google released a classifier called InceptionNet back in the 2010. Yeah, I couldn't say the date precisely, but so this huge classifier that was trained on a huge data set is able to classify images according to a bunch of classes they have. For example, a cat, a dog, an elephant. I'm not sure about what classes this dataset really contains. But anyway, so we have an inception net, and the inception score was introduced in the 2016, I guess. And the idea of the inception score is that it allows you to give a metric to your image generation, right? Because it is a problem to give a metric about how well some model is able to produce an image. How would you want to do this? Well, basically you would want a metric that captures the notions a human would see in a picture. So, for example, now I guess it has been more difficult with recent technologies, but back in the days when you were seeing a generated image, well, it was obvious it was generated, right? But what exactly makes a human know that a certain image is generated? Well, it's not really easy to theorize it. And so Google introduced the inception score, which basically tells you which basically is a metric which they claim is highly correlated to the human judgment. And how does this work? Well, you have this image inception net classifier, so image classifier, and so which is basically, okay, we take an image here and then we use various convolutions and pooling layers. I'm not too sure of how the architecture looks like. And then basically at the last layer you have a number of neurons equivalent to the number of classes you have. And classes with a softmax activation function, which will basically map all the values of your neurons to probabilities. And so what it tells you basically is, okay, I have an input image here from my dog. I'm really bad at drawing, but okay, you get the idea. And then it goes through the network, and then after the softmax layer at the index of the class dog, so imagine it is the last neuron here, well, there will be a high activation, for example 0.9, and then all the rest 0.1 is shared between the other classes. And it tells you basically, okay, this image is a dog. So basic image classifier, right? And so for the inception score, what they do is to compute the KL divergence, so Kullback-Leibniz divergence, which is a measure of how close two distributions are from one another. And so here the distributions they will compare would be the label distribution and the marginal distribution. So let's generate randomly 30,000 images. All right. So sorry about that. We generate 30,000 images. And then each of these generated images, we will pass them to the inception net, and thereby generating 30,000 times probability distributions over your n classes. Right? The marginal distribution is defined as the average of your probability distributions among your 30,000 images. And basically, if you have an image generator which is able to generate all kind of classes, which is what you would want, well, you would have a marginal distribution that looks like a uniform distribution, right? So this means that your generator is able to generate whole kind of stuff. But what you also need, you cannot only with the marginal distribution define whether your generator is good or not, because the average probability distribution could look like this, but it doesn't mean that each individual probability distribution doesn't look like this as well. And this, we won't want this, because we would like sometimes our generator to generate a dog, sometimes a cat, but not always something between a dog, a cat, and all the other classes you have. And so that's why we need the second notion, which is the label distribution, which is, well, the probability distribution resulting from one image flowing through the ImageNet. And this label distribution, you want it to be like this, basically. To say, okay, there is 0.9 chance it's a dog, and then 0.1 other classes. So basically, we are pretty sure your algorithm generated dog. And so to have these two behaviors combined, well, how a way to measure this, it's to compute the KL divergence between these two distributions, as I just said. And then the KL divergence, it is defined in the discrete space as this. So it is negative times the sum over your discrete points of the probability P of a given point times the log of the probability Q over a given point divided by the probability P over a given point. So that's the KL divergence in discrete form. And so what you have here is, imagine we have the behavior here above, right? Well, then this would look like if Q is your marginal distribution, right? It is not a symmetrical, this divergence, KL divergence. So P the label distribution, Q the marginal distribution. Well, if you have a behavior like I have drawn above, well, this would be the logarithm of something pretty big, right? For the class dog, for example. Um, so yeah, let's say for when x is equal to dog, well, then you would have p of x, which is pretty big, right? Let's say 0.9, and then imagine you have 10 classes and the marginal distribution is uniform. Well, then you would have times the log of 0.1 over 0.9, which is well, something very negative, and so which would make this something really positive. And then for the other classes, well, it would be well, yeah. And so what I mean by this, so yes, sorry, basically what it measures is how different these two probability distributions are. If you want to dive a bit deeper into the KL divergence, you can have a look on your own. And so basically where I wanted to come at is that the KL divergence used on the output layer of the ImageNet is pretended to be a good estimation of the quality of the generated image, but well, you can quickly think at a lot of limitations of this kind of metric, right? The first one would be that if, for example, you use your generative algorithm to generate different breeds of dogs, so it will only generate dogs, and I think the ImageNet was trained on the various classes with various animals, but with only one class dog. Well, then of course your label distribution and marginal distribution would look like something like this, right? With here your class dog, and so you will have a very small inception score, but it's just that your generator doesn't match what your inception net was trained on. Okay, so anyway, and then yeah, basically that's the problem about the inception score. Now finally, but well, still it is considered as a good metric, but you need to combine it with other metrics like the FID score. FID score, what is it here? I will make up some space here on the right, I guess. Anyway, this was not a very beautiful drawing. The FID. Again, the FID was built upon the inception net, I think. And so basically here the idea is to make your generated images flow through your network. See something like this, and then instead of taking your last classification layer, you would look at the pre-final layer. And so the pre-final layer basically, so is the layer just before the classification layer, and basically it should contain a lot of information about your image, right? What is contained in your image, but in a macro point of view, I would say. So it is not really pixel related, but it would be more macro related. And so what you want here is to have the way they think at it here is to say, okay, you would want your generative algorithm to generate images which look like the images it was trained on. And so you would have your data, which you would divide in a train set and a test set. So train set and a test set, and then so you use a train set to train your generative algorithm, and then you would pass the images of your test set, and you would pass them in again in the inception net, and then look at the pre-final layer. So for each of the images in test set is fed to the inception net, and then you would obtain a feature representation of this image by looking at this pre-final layer. Okay. This feature representation should represent the images, and so if you do it for all the images in your test set, what you could do is fit a multivariate Gaussian over these feature representations. Fit a multivariate Gaussian. And this multivariate Gaussian, you want it to be close to the multivariate Gaussian you would obtain by fitting it to the feature representations of your generated images. So you take this feature representation for test and gen, fit two multivariate Gaussians, and then compare these multivariate Gaussians. How can you compare them? You can do it, and that's why how the FID was defined. You can do it by computing the Wasserstein to distance between these two Gaussians. mathematically, sorry about that, mathematically this would result in the FID, which is equal to the mu of your test minus the mu of your gen, where mu is the mean of your multivariate Gaussian, plus the trace of your standard deviation matrices. So the sum of your standard deviation matrices minus 2 times these two same matrices, test and gen, and then you would take the square root of it. So that's not very important here, but I think it is worth it to take some time to understand these two metrics that you tend to see in all the papers nowadays of image synthesis. And well, I know it took me some time to take the courage to understand these metrics, and well, I think they are worth understanding. Whatever. Let's now dive into the paper, and first let's see at what images they are able to generate. So here you can see some synthesis examples or generated samples on the Celeb AHQ 256 times 256 dataset, and here on the Cypher 10 dataset, which consists of images of size 32 by 32 of, I think, 1,000 different classes. And so basically we can see that, yeah, it is able to generate pretty nice looking images for the time anyway. Okay, so let's now dive deep into the diffusion models and what they actually are. So here on top you have graph, a little figure explaining how this works, well, showing you the idea behind it. But first let's read the text here a bit. So, a diffusion probabilistic model is a parameterized Markov chain trained using variational inference to produce samples matching the data after finite time. Transitions over these chains are learned to reverse a diffusion process, which is a Markov chain that gradually adds noise to the data in the opposite direction of sampling until the signal is destroyed. When the diffusion consists of small amounts of Gaussian noise, it is sufficient to set the sampling chain transitions to conditional Gaussians too, allowing for particularly simple neural network parameterization. Okay, so all the idea is explained here. Let me try to explain it in more simple terms. So, first of all, what is a Markov chain? A Markov chain is simply a stochastic model that defines a sequence of events such that each event is only defined according to the previous event. So here, if we define our data points x0, x1, x2, and so on until xt, well, what we will have is a Markov chain that allows us to compute x1 knowing x0, x2 knowing x1, only using x1, xt, only knowing xt minus 1, only using xt minus 1. And what we have here, if we consider x0 to be our original image, I will put it like this, of a man, well, our forward process will define is a process, Markov process, that will gradually add noise to your original image. Okay, first a little bit, then a bit more, in order to finally only have noise. That's our first Markov process, and then our second Markov process is what they call our diffusion probabilistic model, which will take noise and then finally build some image of here, kind of fork, let's say. But what's important to understand here is that both processes are stochastic, and what this means is that if you start from some specific noise over here, well, you will not always get the same image, right? Because of the stochasticity of the processes. Let's write some equations upon it, but first of all you can see the little image here, which translates what I just said, basically. So you start from an image x0, you have what they call the forward process, which is defined by q xt knowing xt minus 1, and then the probabilistic diffusion model p theta, where theta are the parameters of our model, which generates xt minus 1 knowing xt. Alright, so let's dive a little bit into the math here and understand what's happening. So, diffusion models, sorry, let me pick up the highlighter. Diffusion models are latent variable models of the form pt x0 equals the integral of p theta of all your latents, where you take the integral over all the latents apart from x0. What does it mean here? Well, it will, for each x0, which is an image in your space, so x0 here is a vector. Imagine you have a 16 by 16 image, you flatten it to obtain that will make 196 vector, a vector of 196 elements of, well, of images. Images, what are they usually? They are either RGB images, okay, so which are composed of 3 channels, right? Like this, 3 channels, all containing values between 0 and 255. Alright, so here that would make 196 times 3, but if we are on a grayscale, okay, let's work with 196 here to make it easier, but I think you get the idea. What does this term mean, p theta of x0? It will give you the probability of generating the image x0 starting from some point xt that was sampled from an isotropic Gaussian distribution. Okay, and so using your diffusion probabilistic model, well, you have xt, all right. So here it is, p of xt, and then the probability of xt minus 1, so big T minus 1, probability of x of big T minus 1, as we are working with a Markov chain. Well, it is probability of xt minus 1 knowing xt, alright, and then for small t you can define it for every t as this. And so this probability can be rewritten in this way. As we are working with Markov chain again, all the different probabilities are independent, and so you just take the multiplication for t equals 1 to big T of this probability. All right, and then here they define P, so your diffusion probabilistic model as a Gaussian distribution. So here the notation is maybe a bit weird. It's a Gaussian distribution defining xt minus 1, which so to define xt minus 1 we will sample from a Gaussian distribution with mean mu theta and with covariance matrix sigma theta. Okay, so for now it's just they lay down some hypothesis. So they define the diffusion probabilistic model p theta as a Gaussian distribution. They say they start from an isotropic Gaussian distribution for x big T, and now what they would want is to, for each point in our data set, well, maximize the probability that our diffusion probabilistic model would generate it, right? And how can you write it down? Well, you can look at the log likelihood. So this is the likelihood of generating x0 with your diffusion process p theta, and so we can minimize this. Minimizing this and setting it as an objective tells you, okay, if I have a data set with different kind of labradors, I want to have a high probability with my diffusion process p theta to generate the labradors. Okay, so that's our objective. Now the forward process, or our second Markov chain, so this is our generative model, right? And then you will train it with the help of a noising process, or also called forward process or diffusion process. And so this process, as I said before, it adds noise to your original data, and according to a variance schedule, beta 1 to beta t. They define it as again a Markov chain. So the probability following the forward process to generate latents 1 to big T knowing x0 is simply the multiplication of the probabilities of at each step. And then each Markov step is defined again with Gaussian distributions. You see a lot of Gaussian distributions in the hypothesis because it is easy to work with them. And so xt is defined as so the distribution over xt is defined as a Gaussian distribution with mean xt minus 1 times 1 minus beta t and with variance beta t. Why now do we use these variance schedules? Well, what you would want to do basically is to have one process which will do noising, so the forward process, and one process which will do denoising. But so you want one to be so your diffusion probabilistic model, your generative model p theta, you want it to be kind of the opposite of your noising process q. How do you do it? Well, you map your images, all your images from your data set. So your image x0, you map it to noise, and then you want to map it back to another image, which is possible. But here you kind of always want to work with the same thing, right? They put they said that they want to learn the reverse process p of xt starting from a Gaussian isotropic Gaussian distribution. And so you want your forward process or your noising process to map to an isotropic Gaussian distribution as well, because if for example, let's take an extreme example, but it's I will write it here, sorry. If, okay, imagine we have some space here. Okay, I will kind of draw spaces, it won't be really beautiful, but anyway. If you have your noising process that takes your images here, that maps to a space, and that maps it to here, to this circle. And then you want to learn a reverse process, but that starts from here, P. And you want it to generate the same kind of images. Well, it doesn't really make any sense, because you want one to be the opposite of the other one. But if you don't start from the same distribution, well, it doesn't seem to make any sense. Well, that's my understanding of it. So basically, to come back to the variance schedule, what you would want is to, when t is very high, well, you want q of xt to be equal to this. And so in order to have the mean which goes to 0 and your covariance here to go to 1, well, to the identity, well, you need this to be smaller than 1 and this to be bigger than 0 and smaller than 1 as well. Yeah, I think it should be something like this. Okay, anyway, so we need these variance schedules, and now we want to maximize the likelihood of generating each image x0. And here the mathematical the math behind it is a bit long, but you can find it in the appendix of the paper. But basically you arrive at an interesting thing, which I will show you just after this. Here they lay down a formula which is interesting, which allows you to sample a point xt directly from x0, because it's you only add a successive Gaussian noise, so you can directly add a Gaussian noise. Yeah. Alright, and now finally when you derive the mathematics behind it, oh, and sorry, they use a variational lower bound. So they say that basically you want to minimize, sorry, like this to be better. Alright, they want to minimize this, right? Well, they say this is always inferior to some things, and so, well, the idea is pretty easy. If you have a function f of x which is always smaller than a function g of x, well, you can minimize g of x in order to minimize f of x. Anyway, so by using this variational lower bound technique, they arrive at this expression which they want to minimize. And here, well, it's pretty interesting. Again, they say we arrive here at minimizing KL divergences. The LT term here basically tells you, okay, I want the probability distribution from which I will sample my points xt to be as close as possible to the distribution I would get from the noising process Q, starting from x0. So that's basically what I said with the different spaces, which, well, sounds pretty intuitive to me. Here what they say in the article is basically that they want to learn your I forgot how they name it, their variance schedules. So basically this is not learnable and you cannot do anything about it. So where we will have really some interesting things to do is with this term. So what do we find in this equation? Well, we find the KL divergence between so my reverse process 0 and so my denoising process p theta. And here, well, it's pretty interesting and pretty intuitive again that they arrive at this result, because they say basically, okay, well, I want my denoising process to be as close as possible as my real reverse process. And the real reverse process, well, they basically are able to obtain it using Bayes' theorem, and they are able to define it. So knowing xt and x0, they are able to define it as a Gaussian distribution which is centered in mu t and with covariance beta t. And then here is the definition of mu t. Well, all the alphas, so alpha and the alphas are basically defined upon the betas, so well, it just there when you derive it, but let's not focus too much on it. And basically the mu here depends on x0 and xt. And so what we finally have is that, okay, my denoising process, which I considered being a Gaussian as well, I want to minimize its KL divergence with another Gaussian. And that's pretty easy because the KL divergence has a closed form between two Gaussians. And so finally it tells you what? It tells you, okay, I want or means to be as close as possible. Here, so I don't remember if I already said it, but our covariance matrices, they could learn it. Here they choose to simply set it to sigma t squared times the identity matrix. Another paper later studies the effect of learning these covariance matrices, but here for simplicity they just don't learn it, and finally it works really well like this, even without learning it. So if you kind of remove everything related to the covariance, as we don't learn it, so we want to minimize this basically. Right, here it is. And so here, what are the terms here? Well, it is simply yeah, okay, well, it's basically a derivation of mu t knowing the formulas of mu t described above. Anyway, it's what I said. They want to approximate this mu t tilde with mu theta. And so mu t must predict mu theta, which can be rewritten like this. And so basically, in order to be able to predict mu theta, what you need is to predict the original image, because this x theta xt minus beta t times eta, which is some sample from a Gaussian distribution again, which is defined here. Well, it must predict the original images, but here what they noticed and what appeared to work good is that from your noisy image, well, either you try to predict your original image or equivalently, you can just predict the noise on that image. Well, it's the same problem, but they found out that predicting the noise directly makes it more stable and results in better training. So they will finally try to predict the noise here. And so they can write the mean of the reverse diffusion process depending on xt and t as this, where E theta is the prediction of the noise at step t by your model. So your model won't try to directly predict the original image, but they will try to predict E theta, and from which you can derive your mean and then simply sample from your Gaussian distribution. Here they say, in order to sample xt minus 1, that follows your Gaussian distribution with mean, mu t, and covariance sigma t squared, well, you can simply write it like this. Right? Here maybe it's not very clear again, but if you have a Gaussian distribution with mean alpha and covariance beta ti, well, you can sample from this Gaussian distribution simply in the following way. Sample, you take alpha plus beta t times z, where z is sampled from an isotropic Gaussian distribution. Alright, this is what they call the reparametrization technique. They use it a lot in the theory of diffusion models. So yeah, that's basically it. I forgot to talk about the last term we had in the equation. Basically, this allows you to create a when working with diffusion models, and each of your model that will predict the noise in your images, it will work with images that have been scaled from discrete integers to linearly to -1, 1. And so in order to build your in order to compute your log likelihoods, well, you want your log likelihoods to be computed on real images, and so you need to bring it back to 0 integers from 0 to 255. So that's basically what they propose here. Yeah, for training, maybe we can quickly look at it. For training, what they would do is choose an image from your original data, select a random step and some noise, so you can generate the image generated by the forward process in the following manner. So that's xt, and then you would do gradient descent on the estimation of your noise here. You know the noise because you sampled it, and you will do gradient descent on it. And then for sampling, well, simply you start from x big T and then progressively create new images with this equation as we saw below. For the experiments, they say they take T equals 1000 for all experiments. They show that with T equals 1000 and your variance schedules going from 10 minus 4 to 0.02, well, you have the KL divergence between your forward process at step big T, so at step 1000, and your isotropic Gaussian distribution, which is at 10 minus 5, so very close to 0. And then the model, this I find it particularly interesting as well, that they really almost never talk in this paper about what model they use, right? They never talk about any architecture. Anyway, here they are talking about a unit backbone using group normalization with transformer sinusoidal position embedding for the time, and also self-attention. They added self-attention in their unit. So yeah, now I think we can move to the generation process. Here is something pretty nice. Here are some examples of generation on the CIFAR 10 dataset. So you can see progressively along the time, well, you start from your pure noise there, and then progressively you will generate real images. So yeah, that was it for my first paper review. I hope I was clear and that I could make you understand how DDPM works. My ambition is to go deeper into new papers about diffusion models, because, well, I noticed there was a big lack of explanation of these new technologies on YouTube, and well, on a mathematical point of view at least. And so I thought it would be interesting to propose it on the platform. So yeah, don't hesitate to well, give your impression on this video and maybe some advices. I know the sound was not very good, probably because I simply recorded it on my computer. But well, if it happens to interest you all, I will do many of these videos and try to improve my explanation with time as well, of course. Thank you.